Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistance. And today we'll be discussing significant figures. So here are some of the rules when dealing with significant figures. Any digit that is not zero is considered significant. Zeros between non-zero digits are significant. Zeros to the left of the first non-zero digit are not significant. If the number is greater than 1, then all zeros to the right of the decimal point are considered significant. If the number is less than 1, then only the zeros that are at the end and in the middle of the number are significant. And zeros at the end of a large number without a decimal are not significant. So let's look at some of our examples. And here we're trying to determine the number of significant figures in the following measurements. So the first one, we have a 5, 9, and 6. They're all non-zero numbers. So it's 3 significant figures. Pretty simple. Again, we've got 5 and 9 are non-zero numbers, but bear in mind that one of our rules states that zeros between non-zero digits are considered significant. So that 0 right there is also significant. So again, we have 3 significant figures. This one down at the bottom is 0.965, 3 significant figures. Again, non-zeros are always significant. Let's look at the next one. The next one, we have 2 non-zeros, 8 and 7. And there's a 0 right before them, but all of this is after the decimal place. If you recall, one of the rules states if a number is less than 1, then only the zeros that are at the end and the middle of the number are significant. So if there was a 0 out here after the 7, it would be considered significant. But because there isn't, we do not count that as 0 as significant. So the 0 up front is not considered significant. So there's only 2 significant figures here. The next one, our next number is 2.650 times 10 to the 22nd atoms. We know that to be significant to 1, 2, 3, 4 places. That 0 following is indicative of a significant figure. Now you're asking yourself, well, hold on, why is that 0 significant, but the other zeros were not? Well, that's because this number is actually a very large number. And so we're going to count any digits that are included inside the multiplication as being significant. In this particular case, we have 4 significant figures. This next one provides somewhat ambiguous terms. We have 6,000. There's no decimal place there. We have 6,000. There's no decimal. So this could be any number. Generally speaking, if this was presented in a problem in class, you would just call this one significant figure. And it would just be 6,000. Or you could easily rewrite this as being 6.0 times 10 to the third milliliters. And that would be 2 significant figures. Or it could be 6.00 times 10 to the third milliliters. And that would be 3 significant figures. Or it could even be 6.000 times 10 to the third milliliters, which would be considered 4 significant figures. But for the sake of argument, we're going to just stick with the 1 significant figure as our answer for this particular problem, because we're not given the decimal place. So let's do some light arithmetic using. In this particular case, we have the large number with grams and the small number with grams. And the large grams has only 1 significant figure following the decimal, and the small has 4. For the purposes of precision, we're going to only stick with the least amount of significant figures following the decimal, which means we're only going to have the 1. So, in this particular case, we're going to deal with adding these two figures together and making sure that we round to the nearest 10th position. So the answer to this is 17,653.4 grams. Again, we're sticking with the 10th position. The same is true when you're subtracting as with when you're adding. So we have 55.27 liters and 3.148 liters. Well, we only have 2 significant figures following the 55, and we have 3 following the 3. So we're going to stick with 2 significant figures, or to the hundredths place when we do our rounding. And after doing the arithmetic, you'll find that this total is 52.12 liters. Again, focusing on 2 significant figures following the decimal place, or just rounding to the hundredths place. Let's do a little multiplication and division. 7.15 meters times 6.4512. Well, whenever you're doing multiplication and division, you want to look for the value that has the least number of significant figures. And that is the number of significant figures that your answer will have. So in this case, we have 3 significant figures and 5 significant figures. So sticking with the least, we're going to have 3 significant figures in our product. So when you do the arithmetic out, you'll find that the total becomes 46.1 meters. Very simple. This next one has 3 significant figures and 3 significant figures. So we don't have to think too much to get the appropriate number of significant figures in our quotient. So if this looks familiar to you in any way, it's because it should. Kilograms is a measure of mass, and milliliters is a measure of volume. Mass over volume is density. So this problem right here is dealing with density. So we're going to take our kilograms and divide by milliliters, and when you do so on your calculator, you'll find that the answer comes to be 0.00118. That's keeping to 3 significant figures because that's the least amount in either of the 2 terms, the initial terms. Generally speaking, we want to try to write numbers in scientific notation. So in this case, it would be 1.18 times 10 to the 3rd milliliters. That's it for that. Not too complicated. One more problem, and this one deals with scientific notation itself. And there's a lot of ways that you can deal with this, or at least there's a couple of ways you can deal with it. But the biggest issue comes to be that we know how to add and subtract and multiply and divide significant figures. But this little 10 to the 4th and 10 to the 2nd power are a little vexing. It's very simple, no need to get too complicated. The easiest way that I find to do this is to convert one into the other. And it doesn't matter which way you do it. I'm going to choose the 2nd term and change it to 10 to the 4th power. And to do so, you simply move the decimal place 3 spaces to the left. So our new value would be 0.0165 times 10 to the 4th centimeters. And then it's just a matter of adding the 2 together. So 6.74 times 10 to the 4th centimeters plus 0.00165 0.0165 times 10 to the 4th centimeters. And when you sum those two values, keep in mind that we only have two significant figures following the decimal place. So we're going to keep to that after we've done our adjustments for scientific notation. So the end result will only be 6.76 times 10 to the 4th. By converting it to both of them to 10 to the 4th, we don't have to worry about the scientific notation unless the value became larger than, equal to or greater than 10, at which point you would just simply move it over 1, or you could just leave it as it is and keep it at 10 to the 4th. Okay. That's it for significant figures. Thank you so much.